Welcome to part 2 out of 2 of functions and graphing. This is also part of the bigger playlist, Prerequisites for Calc BC. If you want to check out the first topic I covered, it was algebra review, so that's already up. Otherwise, let's dive in.
So I'll kind of walk us through a couple examples, and then hopefully we'll get a good intuition behind what a composition is. So let's call a function f of x. Let's call it e to the x. Hopefully you're familiar with this. It's just the exponential graph. Some things I'd like to point out. This x here and this x here are the same thing. So whatever's in this parentheses goes into the input value in my function. Here's the input value in my function. Here's what's between the parentheses. Those two are the same thing. So if I had f of 0, what would I put in for x? Well, I have a 0 between the parentheses, like I had an x in between the parentheses. So now I put, instead of this input x, I put the input 0. Now I have f of 0 equals e to the 0. These two are the same. This is the input value, and this is the input value of the function. Now if I picked something more abstract, like f of w, my input value, instead of having an x and an x, or a 0 and a 0, now I have a w, and hopefully you can see the trend. Now I have e to the w. Whatever is in the parentheses is my input value, and whatever the input value is replaces the input value in the function. So here's the input value in the function x. F of x equals e to the x. This 0 replaced the x, this w replaced the x, and I can generalize this to anything between the parentheses. So if I had x squared plus 5, f of x squared plus 5 equals e to the, and then you just replace this whole thing in parentheses with what's in your input for the function. So it's kind of like a Where's Waldo? You know, like e to the x, it's easy to find where all the x's are, but if I had a weirder function like x cubed over root 5 minus x as g of x, let's call it. If I wanted to find g of, let's just say, x plus h, what would that be? So now you just have to look and find, it's kind of like a Where's Waldo of where all the x's are, and wherever you find an x, you just plug in what's between the parentheses and replace the whole x with what's in the parentheses. So I have g of x is here. G of x plus h looks like, instead of x, I have x plus h cubed. This is the input value here. This is the input value here. Over square root 5 minus, and now instead of x, we have x plus h. 5 minus x plus h. And there you go. So compositions, we can eventually get to the level where we have f of, and then as our input value, instead of an x, a 0, a w, we have a whole other function, g. So now we have f of g of x, where our input is a whole entire other function. So if we wanted to write, if we kept our function e to the x, if we use this for that, we would have e to the g of x. And this is kind of the intuition behind what compositions are. Sorry about that. Behind what compositions are. So you just take whatever's in the parentheses, that's my input, and I put it for any input I can find in my actual function. So here the inputs were kind of nested around, like there's an x, but for e to the x, you just take anything, there's the x, 0, 0, w, w, x squared plus 5, and take the g of x and plug it wherever you find an x and replace it. So if I kept my f of x the same, if I kept it as e to the x, I'll move this up, f of x equals e to the x, and I called a different function g of x, sine squared x. If I wanted to find f of g of x, I take whatever my input is for f and put that in wherever I find an x. So if f of x equals e to the x, f of g of x now would equal, I put the g of x in wherever I find the x. So f of g of x equals e to the g of x, but we know what g of x is because we just defined it right there. So e to the g of x we can actually write as e to the sine squared x. And if we wanted to go the opposite way, we could write g of f of x And so if x is our input here and x is our input here, I would put an f of x where I see that. But we already know what f of x is, it's e to the x, so I just replace every x in g of x with the function e to the x. So g of f of x would equal sine squared of e to the x. So hopefully that gave you a little understanding behind how compositions work. They come up a lot in Calc. Here's the definition of a derivative where it would come up, and it also comes up with like chain rule and stuff. But if we run through this example, if I have f of x equals x squared, how would I find f of x plus h minus f of x over h? So let's just try and do that. So f of x plus h, we just plug in x plus h for x. So we have x plus h squared minus x squared over h. The most common mistake with compositions is not like including parentheses around the input term. So here's the input x plus h. So instead of writing that as like x squared plus h or something like that, make sure your whole input is x plus h here. So x plus h, the entire thing is squared. But if we want to FOIL that out, that comes out to x squared plus 2xh plus h squared minus x squared over h. And this is just straight up algebra stuff that we looked at a few videos ago. X squared minus x squared, those go away. You got an h and an h and an h. So this finally comes out to 2x plus h. You're going to have to do this quite a bit in the beginning of the derivative learning. I think that's like chapter 3. But here's kind of an introduction. So compositions kind of give us a good segue into categories of functions. This is just going to be like interesting functions, unique functions, what makes them unique, different properties about them. But starting with even functions. An even function is defined as a function where f of negative x equals f of x. Now, this may not make any sense, but what it means is that if you have a function f of x, if you plug in a negative x for every x that you see in f of x, you should get out the same function that you started with. So if we were to pick a function, see if it's even, f of x equals x squared. If I were to plug in negative x for every x I see, so if I put a negative x in here, if this were an even function, I would get out the same function that I started with, f of x. So let's check. F of negative x would equal, so we look for every x, and for every x we see, we substitute in a negative x. And so now we have a negative x quantity squared, which if we wanted to rewrite that would be negative x times negative x. A negative times a negative is a positive x squared, and positive x squared is the same as f of x, what we started with. So now we see f of negative x equals f of x, so x squared is indeed an even function. Another way to look at this is plugging in actual values instead of x's. So if we were to plug in f of 3, 3 squared is 9, so f of 3 equals 9. Now, if this is even, which we saw it is, but just play along, if this is even, if we plug in a negative 3, we should get out the same output value, 9, that we did if we plugged in a positive 3. So f of negative 3 should come out to 9. And indeed, negative 3 quantity squared is also equal to 9. So that's another reason that it's an even function. And then we can finally look at it graphically. So if you remember from last video when we talked about transformations, f of negative x is the same thing as reflecting a function over the y-axis. So if I were to interpret this equation here in terms of graphs, what it means is that the reflection of an even function over the y-axis, which is f of negative x, is the same thing as my original function. So reflecting it over the y-axis doesn't change the function. So if I graphed x squared, that's about what it looks like. if I reflect that over the y-axis, this is a y-axis, if I reflect it over the vertical axis, it's going to look the same. This arm is going to exactly replace this arm, and this arm is going to exactly replace this arm. Even though my drawing skills are lacking, you can see that f of negative x, or the reflection of f of x over the y-axis, is the same thing as f of x, what we started with. So reflecting this over the y-axis doesn't change it, which is another reason that it's even. And even functions, they have, you'll see this sometimes, y-axis symmetry. The second type of function is an odd function, and an odd function, different than an even function, is defined as a function where f of negative x equals, not f of x, equals negative f of x. Alright, so if we think about this in the same way, let's see if x cubed is odd. So if x cubed were to be odd, we would look, so this is f of x first of all, we would look at every x, plug in a negative x, and then if this were odd, it would come out to negative times the whole function. So negative f of x is just negative x cubed. So now our task is to see if f of negative x equals negative x cubed or negative f of x. So f of negative x, we look and we try to find every x, and we replace the whole x with this new input value, negative x. So now we have negative x cubed, and negative x cubed can be rewritten as negative x times negative x times negative x, which a negative times a negative is a positive times a negative is a negative. So we have a negative, and then x, we add all the exponents, 1 plus 1 plus 1 equals 3, equals negative x cubed, which equals negative f of x. This right here, the same as this right here, which is the same as this right here, which means that it is an odd function. F of negative x, plugging in negative x for every x we see, came out to negative times the whole function, and there you go. If we want to think about this with actual values, like the other one, let's plug in f of 2. So f of 2, 2 cubed is 8, f of 2 equals 8. Now if we plug in negative 2, we should get negative 8. So negative times this whole thing, negative f of 2 should equal f of negative 2. So f of negative 2 equals, and then we put a negative 2 in for every x we see, negative 2 cubed, and that comes out to negative 8, which is the same as negative f of 2, because negative 8 equals negative 8. Similarly to this one, if we want to think about this graphically, if you remember, f of negative x means reflecting over the y-axis, and negative f of x means reflecting over the x-axis. So odd functions, this is even crazier than even functions, reflecting them over the y-axis, this thing, is the same thing as reflecting them over the x-axis. Reflecting them over the y-axis will give you a function that looks exactly the same as reflecting over the x-axis. So if we stick with our function f of x equals x cubed, here's what the graph kind of looks like. There you go. So f of negative x would mean flipping it over the y-axis. So if we were to do that down here, sorry about that. If we were to do that down here, we would just flip it over there. So now it turns into something like that. This should be the same as flipping it over the x-axis. So this right here was turning it that way, and now we're going to turn it horizontally. So if we did that down here, if we were to flip this upside down, it would look exactly the same. So this is an odd function because if this is f of negative x, or reflecting it over the y-axis, and this is negative f of x, or reflecting it over the x-axis, these two are the same thing, which is another reason that this is an odd function. So similar to how this has y-axis symmetry, This one has origin symmetry. So another property of odd functions is that if you take any point from the origin, so like right there, it should be on the other side of the origin the same distance away, if that makes any sense. So this right here, if I were to draw it the same on this side, would come out to the same point. So every point that you take is symmetrical relative to the origin, in contrast to this being symmetrical relative to the x-axis. And another type of function is the one-to-one and the inverse. So these are kind of related, so I'll just start with the inverse. A couple properties of these. An inverse function is a function where if you graph it, so I'll just pick x cubed. If you graph x cubed, the inverse of x cubed is the same thing as taking that graph and reflecting it over the line. This is a line y equals x. So this comes out to, if I reflected the graph of x cubed over that line, the inverse of it would look like this. So if this is x cubed, how do I get to this? Instead of just taking my word for it, how do I get to this by actually solving? Good question. So x cubed equals y. If I literally switch x and y around, so now instead of x cubed equals y, I have y cubed equals x. And then if I take the cube root of both sides, I would get y equals the cube root of x, or x to the 1/3, which we know is what this graph looks like right here. So if this is y equals x cubed, this is y equals x to the 1/3. These two functions are inverses of each other because their graphs are reflections across y equals x. Another cool thing about inverses, so if I have my normal graph here, if I wanted to find what the inverse graph looked like, I would first of all reflect this graph over the y-axis and then rotate it 90 degrees clockwise, and that would get me to my inverse as well. So if that's kind of hard to visualize, something that's really neat that you can do, so if I draw the function here, I can actually flip my page, and that acts as reflecting it over the y-axis. And now if I turn it clockwise 90 degrees, you can see that this now resembles x to the 1/3, which is my inverse of x cubed. So if I take this, reflect it over the y-axis, turn it 90 degrees clockwise, there's my normal function, there's my inverse, and you can do that all day. So let's take a closer look with inverses. If I have f of x equals e to the x and I make a table with x and f of x, if I plug in 0, I get 1, -1, I get 1 over e, which is, let's just say it's 1/3. And then if I plug in 1, I get e, which let's just call it 3. So if that's my table for e to the x, and I graph e to the x, it would look, I would have 0, 1, 1, 3-ish, and -1, 1/3-ish. So there's the graph that we're familiar with, the exponential. If I were to reflect this over y equals x, what graph would I get from there? So if I take this and put it over here, that is the same as switching the x and the y values. Here I have the x and the y values. So let's switch them around. We have x and f inverse of x. We literally switch, since x equals y with inverses, we switch the x and the y, or the f of x, and then we get a new function, and if we plot those, we should figure out what the inverse looks like. So 1/3, -1, this is -1, there's a point, and then I have 1, 0, there's 0, and then I have 3, 1. So this one would look like that. There's our inverse. So we just reflected it over y equals x by looking at the table of the f of x and just switching it around and then plotting what we found from that. So there's y equals e to the x. Now what what do we have here? Well, hopefully you remember from the functions and graphs part 1, this is the graph of y equals ln of x. So now we know our inverse is actually natural log of x, which makes sense because these two are kind of opposite operations. So if we take our definition of, or our property of inverse, that f of f inverse of x gets us what we started with. Using these two functions, if I take f of f inverse of x, there's f of x, e to the, and then f inverse is what I plug into x, and f inverse is ln of x, e to the ln of x. If you remember from our log and exponent rules, these two cancel and go out to x. Similarly, if I were to take f inverse of f of x, f inverse is ln of x, so ln of, and then what I'm plugging in is the whole function f of x. I replace x with f of x is e to the x, so we have ln of e to the x, which again, these cancel, and it just becomes x, which is what we defined here as a property of inverse functions. And I said these were related to one-to-one functions, so I'll introduce that now. So a one-to-one function, if you remember from the beginning of the functions videos, when I was drawing these blobs for the domain and the range, there's the domain, here's the range, function. So I said the only thing that disqualifies a function is if you have one domain value going to two different range values. And I said you can have two domain values going to the same range value, or any amount of domain values going to the same range value. But as soon as you have one domain value going to two range values is when it's not a function. Well, the one-to-one function, what makes that unique is that each domain value has its own unique range value. So if I were to graph this situation here, I would have same range value, same range value, same range value for three different domain values. This wouldn't be a one-to-one function because each domain value in a one-to-one function has its own unique range value. So, you know, right here, this function still qualifies by the vertical line test, right? If I just drew vertical lines, it wouldn't cross anywhere twice. The thing that helps with distinguishing one-to-one functions is the horizontal line test. So if I were to draw a horizontal line, you can see that this isn't a one-to-one function because it crosses this function. Using the horizontal line test, it crosses the function more than once. So a one-to-one function, if we stick with x cubed, since that's a one-to-one function, you can see that if I drew a horizontal line everywhere on this page, nowhere would it cross twice, and also with the vertical line test. So this is both a function, but it's also a one-to-one function because it passes the horizontal line test, and each range value is unique to each domain value. So the interesting thing about one-to-one functions and inverses is that a one-to-one function, its inverse is also a function. So that's kind of the point of this whole exercise. If I had x squared, hopefully you can tell this doesn't pass the vertical or the horizontal line test, it passes the vertical line test. So since it doesn't pass the horizontal line test, it's not a one-to-one function. Since it's not a one-to-one function, its inverse isn't a function. So if we remember, taking inverses is the same as reflecting it over the line y equals x. So I take that over here, that would turn into a sideways parabola. And obviously this doesn't pass the vertical line test because, yeah. So that's kind of why the horizontal line test works, because if you take its inverse, it's not going to pass the vertical line test. So one-to-one functions, their inverses are also functions, and that's what makes them unique. So the last two functions are piecewise and periodic. So right here I wrote down the definition of a periodic function. So a periodic function is defined as a function where f of x plus c equals f of x. So c is just any number. So this is kind of hard to digest, but if you remember from our translations video, having an x plus a number inside the parentheses means a horizontal shift. So what this means is that if I shift a function horizontally for some length c, if that's 5 or 26 or whatever, if I shift it over that much, at some c value, it's going to look the same as my original function f of x. So then I drew a periodic function, since trig functions are basically all periodic. So if I draw y equals sine x, that's this. If I were to shift sine x over 2 pi in either direction, since this goes off in all directions, if I were to shift 2 pi if I were to shift sine of x 2 pi in either direction horizontally, it would look the exact same as what I have right now. So if I took f of x plus 2 pi for f of x equals sine x, f of x equals sine x, that would equal sine of x plus 2 pi. And this makes sense because, you know, the unit circle is only 2 pi around. So each time I go around, I'm repeating the same values over and over and over, which is why this graph is periodic, because it just repeats the same pattern. And finally, the last function type is the piecewise function. So a piecewise function is a function where along the domain, so along the function, it is defined by different formulas for different parts of the domain. So what that would look like, maybe you've seen this wacky bracket thing before, that's just a piecewise function. So if I did a function and I defined it as negative x for x's that are less than 0 and x for x's that are greater than or equal to 0. So if I look at these are the intervals upon which these different formulas define the function. So this is defined as x is anything less than 0 and greater than or equal to 0, so that covers the whole domain. So if I were to graph this, it's defined as negative x up to 0. So negative x, remember, looks like that. And then that's only up to 0. And then at x is greater than or equal to 0, it's defined as x. And there we go. So that's our piecewise function. It has two different formulas for two different parts of the domain. And if you remember correctly, this is also the function absolute value of x. So absolute value of x is sometimes written as that. It's a piecewise function of negative x and x in two different parts of the domain. And these can get as crazy as you want to get them. This is only two different formulas. You could have, you know, as many as you want as long as the whole domain is covered. But yeah, that's the last type of function.
Thank you so much for sticking through this. I know it was a lot. This is the end of functions and graphing. Next video will be Geometry and Trig, and that will be the end of prerequisites. And after that, we can move on to limits and continuity, and then derivatives, and then wherever the year will take us. But thanks for watching this one, and I'll see you in the next one.